like maybe a lot of people are working on the panic mode, working on the assignment that's due today. This is not usually a good sign, especially not for the first assignment. But anyway, maybe this is a learning experience for some people. They go, oh, maybe I shouldn't leave things to the last minute, which is probably one of the #1 rules of software engineering. Right? Like never leave things to the last minute because you'll hit bugs at the last minute and things won't work. Anyway, that said, so we were talking about starting to talk about temporary objects in the last lecture. And I think we've gotten up to the point where we're about to discuss the very last bullet on the slide. So basically temporary objects, again, they're objects that are created by the compiler. They have no name. They're unnamed objects. There's no name by which you can refer to them, like X or something like that. And they're introduced by the compiler in order so they can do its job, like basically make the code that you've written work, because without it, it wouldn't be able to do things in a sensible way. So we're looking at some earlier examples. I'm going to start out with the last bullet on the slide. So another example of situations in which the compiler may generate temporary objects is when you're passing arguments to a function. So in this particular case, we have a function called func. It's passing by reference because of the ampersand here, passing specifically by reference to const. And it's a double, the value that's being taken here. And then we're passing an integer value of 3 to the function. The issue here is that obviously, I mean, the type of 3, it's a literal of type int. It doesn't even match the type of this reference, right? The reference is a reference to double. It's still a valid function call, but you can see something special must happen, right? Because obviously, x can't refer to that value of 3 because it's an int. So basically what has to happen here is the compiler will generate a temporary object. If it's effectively this line here kind of becomes something that looks like what's commented out in the 2 lines below. The compiler will generate a temporary object, and again, it's not called _temp. It has no name. There's no name by which you could refer to it. But just so that I can write some kind of sensible code that you can understand, I've given a name _temp, and it will initialize with this from the integer value 3. So what you end up with is a double that's equal to 3. And then when the function is called, the reference here that's being passed, this reference to x is going to be referring to this temporary object. It's not referring to the 3, because it couldn't be referring to the 3 directly, right? Because, well, first of all, 3 is just an expression, it's not an object, but aside from that, it's not even of the right type anyways. But because there is a built-in conversion from int to double, it basically does this for you and then passes a reference to the temporary object that's created. Any questions? So this is another example of a situation in which the compiler will introduce temporary objects. Go over to the next slide. Another sort of situation, this is in some sense similar to the previous example. When you're initializing references, which is essentially what happens when you pass by reference, the reference in the parameter list of the function has to be bound to something. This is kind of a similar situation, except now we're not dealing with something that happens to be a parameter to a function, but we have a similar sort of pattern here. We have an integer variable I, which is initialized to some value. Then we try to bind a reference, which is a reference to double, to I. But obviously, this can't really work directly, right? Because I is an int. D is a reference to a double. A reference to a double can't refer to an int. It refers to a double, right? So what will happen, this is actually still valid code, but what will happen is the compiler will secretly, create a temporary object, which is of type double, basically the type that this reference wants. It will then use the variable I to initialize this variable, and then it will bind the reference D to this variable temp, this temporary object _temp. Again, it's not called _temp, it has no name, but just for illustrative purposes, I've given it a name here. And you should never use symbols, by the way, in C++ code that starts either with 1 underscore or 2 underscores. Typically, these things are reserved for the implementation. If you start doing this, God only knows what's going to happen in your code. Because you could have collisions with internal implementation details of the compiler and library, standard library. In terms of the lifetime of temporary objects, in most cases, but not all, and there are some interesting counter examples or exceptions, but in most cases, temporary objects, they are destroyed at the end of the expression in which they were created. This would apply, for example, in this case, I guess, well, we haven't talked about this case yet. I still need to talk about function return. I'm getting ahead of myself. Well, let me talk about function return. I somehow managed to skip this bullet, I think, unless my memory is really getting bad. So function return, when we're returning by value, this is another situation in which temporary objects can get created. We kind of hit this, I think, in the last lecture in an example that I talked about. Here we have a function called getMessage that returns a string. It's returned by value. It's not returning a reference to a string. It's actually returning a string. So it's returning by value. And then we have some other string s, and we're calling getMessage and then taking the result that's returned by this function and assigning it to s. But if you stop and think about it, like getMessage bracket bracket is an expression. It's not an object. I can't pass getMessage bracket bracket to the assignment operator for the thing that I'm assigning from. Like when I call operator equals, the thing that I'm passing for the thing to assign from, I can't give it like the expression getMessage bracket bracket. So what's happening internally, like in the compiler, it will generate a temporary object, and it will take the return value of getMessage and then store it into this temporary object. And then when it calls operator equals, the thing that's passed as the parameter that corresponds to the right-hand side operand of the equal sign is going to be temp. Like in other words, it will basically invoke code which looks something like this. This is like a very, very common sort of case, and one that actually will be quite important one, I guess, in terms of some of the things that we talk about subsequently. But when you pass by value, or sorry, when you're returning by value, you always have this issue about the potential for temporary objects to be created. And I guess now I can kind of finish talking about the last bullet on the slide. So usually temporary objects are destroyed at the end of the expression in which they were created. So like on this line here, the expression that's causing a temporary object to get created is like evaluating s equals getMessage bracket bracket. So essentially, when you hit the semicolon here, like the line's completed executing, that object would underscore temp would be destroyed. This is not always the case. There are other situations where it can have a longer lifetime, like when you bind it to a reference, for example. But in most cases, the lifetime ends when you kind of hit the semicolon or you hit the end of the expression in which that temporary object was needed. So the next slide here, I have a simple example of a very kind of stripped down complex number class that provides some very basic functionality. And I just want to use this as an illustration for temporary objects. The specific details of the class are not that important, but I need to have a concrete example just because in some cases you might care about whether, how parameters are being passed, whether they're passed by reference, and how things are being returned, whether they're returning a reference or returning by value. Otherwise, we might not be able to kind of fully appreciate the example. Anyway, so we have a complex number type, we have some constructors, assignment operators, and so on. Get the real part, get the imaginary part, and then we store them as two double data members. And I guess maybe the most important thing is maybe this operator plus, because this is what we're going to be using. Like in the sample code down below here that's using the above class, we're basically trying to use the binary operator plus to add a plus b, so it's going to be invoking this function here. And part of what we're interested in is temporary objects, like what temporary objects are going to be created. So, but I'm going to look at it in more detail. This is the main function as it appeared at the bottom of the previous slide, even though that's the code that you write. So this is what we actually wrote in our code, but in effect, what we end up with is something that kind of looks like this. In the place where we're invoking the operator plus to compute the sum of a plus b, and then we're taking the sum that results from that and we're assigning it to c. The return value from the operator plus has to be stored somewhere. It can't be, because once that function returns, if it's stored in a local variable inside operator plus, well, it's gone after we've returned. So it needs to be stored somewhere. And the place it gets stuck into is like a temporary object. So essentially what's going to happen here, this a plus b the compiler will generate a temporary object, which I've called underscore temp here. Again, it has no name, but just for illustrative purposes, it's called underscore temp. And the return value of a plus b is going to be stuck into this temporary object. And then when the assignment operator portion of this line executes, when we're doing the assignment, the thing that's being assigned is this temporary object. We're assigning from this temporary object to C. So this just shows you kind of a further illustration of how temporary objects can manifest themselves in code. Another example I want to give, which is maybe a good one to look at, you may often see people giving the advice that when you're using increment and decrement operators, it's preferable to use the pre-increment and decrement rather than the post-increment and decrement. The reason why is efficiency. It makes a difference. I mean, in some sense, although these operators have similar semantics, I mean, at the end of the day, you end up incrementing or decrementing something. They have some slight differences in their semantics in terms of what the expressions involving them are equal to. And because of this, can potentially be a very big difference in terms of efficiency. And it's essentially because of temporary objects, or largely because of temporary objects. So what I have in this particular code example, the counter class at the top here, we have just a basic counter type, so it maintains a count, which is an integer value here. And we can do some very basic things. We can default construct a counter, which initializes the counter's count to 0. We can increment the counter's count. Well, sorry, we can get the count by using this member function here, get count. And then we can also increment the counter. But we can increment it in one of two ways. We can either use the prefix increment operator, like ++, and then the name of the thing that we're incrementing. Or we can use the postfix operator, which is like the variable name and then a ++ afterward. And by the way, the language distinguishes between them, you can sort of see here. The problem is like neither one of them takes any parameters, so it's like, well, how do you distinguish them in terms of the syntax of the language? So in the case of the postfix increment, what they do is they add this dummy integer parameter. I mean, it doesn't take an integer parameter. You can't say ++ and kind of give it a number. But this is the way that it distinguishes. So when you say operator ++ and it takes an integer parameter, this is the postfix version, and the one that takes no parameters is the prefix version. I mean, you can actually look at the value that's passed. I don't think it's actually required to have any particular value, but I just for fun I did it with one compiler and it was always 0. But I don't think there's any requirement for what it should be. But basically you would never use it in practice. But there needs to be a way syntactically to distinguish between these. Anyway, so there is a difference in semantics between like ++x and x++ for the built-in types anyways. And probably you want to mirror this in any implementations of ++ you have for user-defined types. If I say like for the prefix increment operator, so if I say like ++x, so the ++ is coming before the x, the value of ++x is the value of x after I've incremented it. If I say x++, this is the value of that expression is the value of x before I increment it. Both of them increment x, but the value of the expression is different. In one case, it's the value it's the old value that's saved before you increment x. The other one is the value after you've incremented x. And if you think about implementing each of these, one of them is fundamentally more efficient than the other. Because the one that has the value of the old value of x, well, how do you make it the old value? Well, you have to save the value before you increment it, and then return the value that you saved. Whereas if you're returning the value after you increment, you don't need to save anything. You just increment it, return the value. And this is kind of the pattern that we see in terms of the code. If we look in more detail here, the prefix increment operator here, so this would correspond to something like what we have down here. This is the pre-increment operator. This is a much more efficient one. But the reason why it's more efficient is that if we look at what happens here when we call this function, so we say like ++x, what's going to happen, it comes into this function. You're going to increment the count that's associated with this object. So we have the cost of an integer increment operation or integer add operation. And then we just return a reference to this, because if you look, it's returning a reference. And we can safely return a reference here because the thing we're returning a reference to is the object that the user called us with. So we don't have any concerns that while we're returning, this object disappears and now we have a dangling reference. The reference will definitely be well defined. So we can get away with returning a reference here. So returning a reference, there's no copying of anything that happens because we're just returning a reference. So the cost of this particular function call here is there's no temporary objects that are created. And basically we have the cost of an integer increment, which comes from incrementing this count variable here. And then afterwards, after this is returned, then we have to take the value that's returned, which is a reference to x, and we have to assign that to y. So we have the cost also of an assignment operation. And neither one of these operations we can really get rid of. Like fundamentally, we're going to have to increment the counter, and fundamentally, we're going to have to do the assignment because there's not any way to avoid them. But where things get kind of really ugly is if we try to use things with the post increment, then we're doing a lot of stuff we don't need to do. We're doing a lot of extra work, and part of it, largely, it's coming from temporary objects. So if we look at the post increment case, well, one of the fundamental differences here is the return type. The return type here is not a reference type. It's returning a counter. So this means the way that you get the return value out of the function is you have to copy it. It has to be saved somewhere because you don't have a reference that you can just look at the value. You basically have to save the return value in some temporary object. So this is going to require a temporary object to hold the return value. Also, in addition, inside this function, we have what is effectively a temporary object, but it's not actually a temporary object because it has a name and it's not the compiler's variable. But basically, this old is kind of like our temporary variable as the programmer. We have to save the old value of the counter so that we can return the old value when we're done. Because the semantics of postfix increment is that you return the old value. So if you increment it, you have to remember what the old value is so you can return it. So if we look at this function here, like inside this function, we have the overhead of we have to construct a counter. When we reach the end of the lifetime of, well, basically the end of this function, you're going to have to destroy that counter variable. So we have an extra creation and destruction of this counter object. But things get worse than this because this function is returning by value. So the thing that's being returned here, which is old, the only way that the caller has any hope of ever seeing that value that's returned is if somehow it's saved before this function returns. Because the instant you return from this function, old, which is a local variable, it's gone, it's destroyed. So it's too late for the caller to say, what was the value of old after the function's returned, because it's gone, it's destroyed. So it has to be saved somewhere, which is where the reason why there's a necessity for a temporary object, because it's too late to ask after you return from the function what old is, because it's destroyed then. So what the compiler does is it goes, well, I know you're going to be screwed if I don't do this, so what I'll do is I'll copy old into a temporary object in the caller, so it belongs to the caller. Then when the callee returns, that object, the old, gets destroyed, but the temporary object in the caller is still there, so you don't lose the return value. So this is basically what happens here. When you're calling x++, in addition to the construction and destruction of old, which happens internally here, the return value that's returned here, because you're not returning a reference, but you're returning by value, the compiler will generate a temporary object, and it will stuff the value of old into this temporary object in the caller before you return, before the caller, the function that's being called operator ++ returns. When operator ++ returns, old is destroyed, but we safely have tucked into our temporary object in the caller the return value. And then that temporary object is used for the assignment operator, which is assigning to y. But if we kind of tally up the cost of doing things in this way, we have one temporary object that's being created and destroyed. So there's a constructor call for it, a destructor call. So we have one constructor call, one destructor call. We also have effectively what is like another temporary object, but it's not really like a temporary object in the strict language sense, but it's kind of like, you know, sometimes loosely we talk about temporary variables in our program that we make. It's temporary in that sense. Like the only reason that we're creating this thing old is that we have to save some value so we can remember what it is later. So in some sense, it's just another temporary object, but not like a compiler temporary object. Anyway, so we have to construct this thing and destroy it. So we have like two constructor calls, two destructor calls, temporary being created, and then the other stuff that we have to kind of fundamentally do. We have an integer increment and an operator equals to do the assignment. But like the cost of doing the postfix increment is much, much higher than the cost of doing the prefix increment. And now imagine that usually when you're using these operators, you tend to do them in loops, right? So probably you're executing that line millions, billions, trillions of times. And the cost of doing it in one case is so much more than the other, and you're doing it millions, billions, trillions of times. It can be quite significant. Sometimes it could even maybe become a bottleneck in some particular cases. So this is the reason why sometimes, I just want to use this as an example, because sometimes people will say, you know, it's better to use prefix, increment, and decrement rather than postfix, and people just kind of blindly follow that, but they don't really understand, well, why does it really matter? This is essentially the reason why it matters, largely because of temporaries, or kind of things that are kind of like temporaries like this, like inside this function, we have to essentially save some state and then so that we can later return that state. Anyway, so this is why we want to avoid, well, why we would prefer to avoid postfix increment and decrement if we can. Any questions? Okay, so that's kind of a brief spiel about temporary objects. The next thing I want to talk about really is about moving and copying in the language, and largely a lot of the other kind of more technical stuff I'm going to be talking about pertains in some sense to copying, moving, and some other optimizations that allow us to eliminate temporary objects in some cases. So if we have two objects, you know, x and y, and we want to propagate the value of x to y, there's two choices in C++. We can either do this by copying or do this by moving. And the only difference between copying and moving, copying makes, well, copying is, copying makes the guarantee, maybe putting it this way, copying makes the guarantee that when you propagate a value from some source variable to some destination variable, it won't change the value of the source. The thing that you're copying from will be guaranteed not to be changed by the operation of copying. Whereas moving makes no such guarantee. This is the difference between copying and moving. If you move from one object, like a source object, to a destination object, after you've moved the value, you're guaranteed the destination object had what the source had before. But what you're not guaranteed, unlike in the case of a copy, is there's no guarantee that the value of the source is what it was originally. Its value can be totally mangled. Normally, you'd want to make a guarantee that it's valid, but you make no guarantee about what that valid value is. So the source will have some value, but you don't know. So effectively, you can't really do very much with an object that you move from. The only thing you know is it has some valid value, but you have no idea what it is, which makes it, practically speaking, not very useful. Often for containers, it might be an empty container. You move from one container to another, one vector to another. Often the consequence is that you're left with an empty container. But there's no guarantee. It just says, I'm not going to tell you what it is. It's just some valid value. And then that gives kind of the maximum latitude to the implementation to define what the remaining value is from the source of a move to be whatever leads to a most efficient implementation. So copying versus moving has certain implications in terms of efficiency. But this is not the only reason. There's some types where copying doesn't make sense. Like, for example, you have like C in and C out, the standard input and standard output streams. What would it really mean to copy like a standard input or output stream, or maybe something like a mutex, where you're doing like a multi-threaded coding, and a mutex is basically a mutual exclusion, used for mutual exclusion. What would it mean to copy a mutex? I don't really know. Actually, probably a better example is the stream case, though. Like I streams and O streams, like C in and C out. I mean, what would it really mean to copy them? It's not really clear what the semantics would be. Like, how would you define what a copy of an input stream or output stream is? Because it's not really clear that there's any good meaning. Rather than try to give it some kind of really weird kind of meaning, we just say, we're not going to let you copy this kind of object. So there's some types of objects, and O stream and I stream are good examples, where you can't actually copy them, but it might make sense to move them, to move one to another. So aside from the issue of efficiency when we're talking about copying and moving, there's also the issue that you may have some types where it makes sense to move them. Because there's not maybe too many types where it doesn't make sense to move. There might be some due to other limitations you can't move them for other reasons, but generally it tends to be the case that most types, probably there's some sensible way you can define moving them, but there might not be a sensible way to define copying, in which case we define moving but not copying. So this is another reason to make a distinction between moving and copying, because some types may only permit moving and not copying. Then we have to care which one are we doing, because if we do the wrong one, nothing's going to work. We'll get a compiler error because the type doesn't provide the ability to copy, and we're trying to copy. So this is just kind of illustrating things in pictorial form. So like if I have a source object A, then I'm trying to propagate a source object called source and a destination object called destination. I'm trying to propagate the value of A to B. After a copy, the picture looks like this. And the important thing is that the source is still having the same value we started out with. However, with the move operation, if we start out with the same sort of picture before we move, then the difference with a move is that we don't know what the source object is equal to after the move. Now, a common misunderstanding is nothing that says it has to be different. It could be the same. But what's important is there's no guarantee. You can't assume it's the same. Sometimes students are surprised when they're using some type and they actually look at what the value is after a move and they go, but it is the same. It didn't change. The move operation doesn't promise it's going to change the source of the move. What it doesn't do is it doesn't promise that it won't change it. So it might change, it might not. But usually the fact that you can't be guaranteed that it won't change is enough to say, I don't want to use that value, like in practice. So that's an important thing to understand. It's most correct to say that it doesn't make the guarantee that it won't change the source when you move it. It might change it, it might not, but because you don't know, you can't assume that it won't change. And normally it's defined in such a way, move operation, that the value after you move from something, it's guaranteed to be a valid value. Because you don't want something to, like, you program to seg fault or something when you try to call a destructor for that object that you moved from. So you want it to have some kind of sane state, but there's no guarantee about what that sane state is. Any questions? And I apologize, here we're kind of jumping around between different parts of the lecture slides, but at least the slide numbers should match the ones you have, which will maybe make it a little bit easier to navigate around. So here I have an example. I want to illustrate kind of the benefits of why we might want to move versus copying. Like, why should we even have like two different ways to propagate values between variables in the first place from an efficiency point of view? If you've only been implementing very simple types in C++ so far in the programming that you've done, then there's not going to be any apparent reason why a move would be helpful. Because like for very basic types, often there is no benefit really. A move would do the same thing as a copy. But once you start to get into more sophisticated data types, then you're almost guaranteed a move will be much more efficient than a copy. Like going from, say, a linear operation to a linear time operation to a constant time operation or something like that. Like the difference is extremely large. So what I want to use for an illustrative example is just a simple character buffer. So we have like a class called buffer. We have a pointer to some chunk of data which holds the characters in our buffer. and then some count, which is telling us how big our buffer is. So in terms of the picture, we have a data structure which looks something like this. So we have a pointer which points to some chunk of memory which has n elements in it, where n is the size. And then what I want to look at here is how could we implement moving? How could we implement copying for this type? I'll start out with copying. I think that's what's on the next slide, because it's maybe the more straightforward thing. So imagine that I have like a source object called src and another object called dst, where both of them are these buffer types. And I want to propagate the value of source to the destination using a copy type operation. How would I implement this? Like, how would this work? Essentially, the code that would be associated with it would look something like what's shown at the top of the slide. So this is kind of the before picture. Above this horizontal line is before, and then below the horizontal line is what things look like after we've done the copy operation. So effectively, what's going to have to happen here for the copy operation to work, we want to make sure that the data in this buffer here is in this buffer after all is said and done, after we've done the copy. So what would we have to do to make sure this happens? Well, we would have to invoke the destructors for all of these objects here, like get rid of them. We want to get rid of them. Actually, I think I said it was a character buffer, so there's no destructors being invoked. But if it was a user-defined type, which is stored in this array here, we have to invoke the destructor for every single one of the elements there, and then free the memory that is actually holding these elements. So potentially you have to invoke a bunch of destructors, which would be like a linear time operation, linear in the number of elements in this buffer, and then you free the memory, which also tends to be somewhat of an expensive operation as well. Allocating and freeing memory is not such a cheap algorithm to have to deal with. And then once that's done, then we have to copy the value of n here into m, because we've probably just changed the size of the array. So we need to be careful to make sure that we've updated now. So this is basically what we have. Oh, sorry, I left out the copying as well. I think I did mention the copy. We have to allocate a new array, which is the same size as this, and then copy all of the elements as well. So if you look up at the top here, we have basically the deletion of the old data array, this thing over here. Then we're going to allocate a new array, which is the appropriate size to hold the thing that we're copying from, which is for a user-defined type. If t is a user-defined type, this is going to invoke a constructor for each one of the elements. I think here we were dealing with a character array, so there's no constructor to invoke. But keep that in mind. If you allocate an array that's a user-defined type, you're invoking the constructor for each element that you're allocating in that array. And plus, we have the overhead of allocating the array itself, like the memory allocator has to be invoked. Then we copy the size, and then we have to copy the elements. So we have a bunch of operations. This one is kind of the killer, I guess, because no matter whether it's a built-in type or not, you have a linear time operation to copy all of those elements. If it's a built-in type, at least the destruction and construction that's happening up above here doesn't need to happen. There's no constructors and destructors for built-in types. But if t is a built-in type, then you have yet more cost that's associated with this. So this is basically what's required to make copying happen. What if we look at the case of moving? How could we implement moving? And there's multiple choices that we could make in terms of how we might implement a move. The example that I'm showing here is probably not the way exactly you would do it in practice. You'd probably do a little bit more, which I'll comment on in a moment. But in principle, this would satisfy the requirements of a move. So essentially what we're doing here is we're saying, so this is, again, the same picture as we had before the move operation happens. And what we want to be true after the move operation happens is that the source has some valid value. We don't care what it is. And the destination has the value that the source originally had. So what we're choosing to do here is we're just basically going to swap the two values, swapping the pointers and swapping the sizes. So we're going to make this pointer here, instead of pointing to this array, it's going to point over to this array. So you can see after we've done the swap, this guy here is now pointing all the way over to this thing over here. And then, of course, this guy here is going to be pointing over to this array here. So you can see here, this pointer is now pointing over to this array. So we basically swap the pointers. And of course, we also have to swap the sizes too, because the sizes might not be equal. So n and m, these values here, have been swapped. Now they're m and n at the bottom. So so this is like a very, very cheap operation. Even if these buffers are huge, gigabytes, terabytes, doesn't matter. We just swap two pointers, swap two integers, we're done. Very, very cheap operation. In practice, though, probably there would be a good chance that you'd actually want to deallocate this chunk of memory here. The reason being is if you only do this, like this would be valid, it would satisfy the requirements of a move, because there's no guarantee about what the source is going to be when we're done. So we could make it just whatever dest was before, the dst variable. So this is valid. But you might actually want to, in practice, actually free this memory and then make the size 0. The reason why is that maybe this src variable never gets used again until basically you reach the end of the function it's in, eventually it gets destroyed. So like maybe you never use it until it gets destroyed. But maybe if there's like a gigabyte of memory allocated to this buffer, it's hanging on to a gigabyte of memory. You know you're never going to use it, and it's sitting there just waiting for the destructor for that object to get called. So knowing that because the user can't rely on the value of source after the move, because again, after a move, you don't know what the value is. So the user can't rely on the fact it has anything useful. So you know they're not going to use it, but you have maybe a gigabyte array that's allocated there. So you might as well just free it. So in practice, it may be for security reasons, like if this was holding up, if these buffers were holding passwords or something, if there was sensitive information, maybe also for that reason, you'd want to like free it when you could or something like that. But anyway, maybe the more important point is that you could be like holding on to this memory, not knowing that it's unlikely anyone's ever going to use it for some fairly long period of time. So why not just free it? But I showed you kind of a simpler version in terms of the algorithm here. You could literally just swap 2 pointers, swap 2 integers. This would satisfy the requirements of the move. And in some cases, maybe you'd want to do this, because maybe you know it's not an issue that maybe you're holding on to this memory, and that might save some time, possibly, depending on how the algorithm is structured. Any questions? So what this slide basically is saying in sort of a nutshell is that we've sort of seen that there's 2 ways that we can propagate values of variables, propagate values from one variable to another, either using moving or copying. And we've seen that at least for some types, the kind of more interesting, more fancy kind of types, it's often going to be much more efficient to do a move rather than a copy. So a reasonable question to ask would be like, could we somehow make the language do the right thing? Like I'm trying to do, propagate the value of one variable to another. Could we define the language in such a way that if a move would be safe to use, it uses a more efficient move. If it might be dangerous to use it because it could maybe break our code, it will fall back to doing a copy. Like, could the language be defined in such a way? And if so, like specifically, how is it defined? Like, what are the mechanics of how it works? So this is what I want to look at sort of in the subsequent ensuing slides. And this is where we get into some kind of gross stuff like value categories and so on. But nevertheless, it's kind of important to get into if you really want to truly understand how moving and copying really work. The basic idea is that the language defines a number of different rules that all conspire together in the language to achieve the end goal that moves happen when they can. Like you prefer a move over a copy, and the moves will happen when they can. And in cases where it might not be safe to use a move instead of a copy, it will use a copy to be safe. And there's a lot of rules in the language that kind of conspire together to achieve this goal, which is what makes it a little bit difficult to understand, because it's not just like kind of one thing. It's a whole bunch of things, a whole house of cards, which is very, very carefully constructed so everything just works the way that you want, at least most of the time anyway. And then there's ways that we can kind of override the default behavior and say, even though compiler, you think it's not safe to do a move here, I don't care, trust me, I know what I'm doing better than you do, move anyway. So there's ways that we can kind of override the default behavior. But what we'd like is we'd like the language to do the right thing in the vast majority of cases so that we don't have to override things. Of course, once we start overriding things, there's the danger that we think we know too much. And we say, compiler, I know more than you, it's safe to move here, and really it's not. And then, all heck lets loose in your code. But anyway, so what we're going to be looking at in sort of the subsequent slides are the rules that sort of conspire together to make things work. But in order to understand that stuff, I have to go through a bit of a long digression talking about what are called Lvalues and Rvalues and value categories and so on, which admittedly is kind of gross. But if you really want to understand this, and also we're going to talk about an optimization called copy elision a little bit later, you really need to have kind of a good handle about value categories to understand that stuff. And it's quite important from an efficiency point of view. So with that said, again, we're jumping to some other section of the slides here, which is talking about what are called value categories. So value categories is a way we can classify expressions in the language. We're not talking about variables here, but rather expressions, like y equals x is an expression, a plus b is an expression, like basically probably almost anything is an expression in the language. And every expression in the language can be classified into one of 3 mutually exclusive categories. These are what are called value categories. And you can see there's like nice cryptic kind of naming, right? There's like L values, X values, and PR values. X value stands for expiring value. PR value stands for pure R value. L value and R value, the L stand basically has to do with like left-hand side. R historically used to deal with right-hand side, but probably forget that I said that, because like now there's not really any meaning attached to R and H, or sorry, L and R anymore. Originally, when the terms were used way back, and this kind of was inherited from C, they made more sense, but now they don't really make sense anymore. So it's better just to think of L value as it's just an L value. There's no deeper meaning to the name, but there actually is. It's just, it doesn't really make sense anymore. And similar with R value. X value actually kind of makes sense. It stands for expiring value, and you see what it is, then it will kind of make sense. And then there's this other thing called there's other terminology that relates to it. So in terms of sort of a Venn diagram or whatever, we have something that kind of looks like this. We have every expression can be classified either as a L value, an X value, or a pure R value, PR value. But then we have two other terms which are kind of grouping various combination of these things. So things that are not R values are called generalized L values, GL values. So a GL value is something that's either an L value or an X value. And then we have things that are either R values or not R, or sorry, that's R values or not R values. Then we also have sort of the opposite thing, which is things that are basically in this dotted line circle here. If we have something that's either an X value or a pure R value, this is called an R value. And a thing that's either an L value or an X value is called a GL value. In terms of the discussion that's coming up, I don't really care so much about generalized L values. These tend to not, at least in my opinion anyway, they tend not to be as important to understand in terms of like a lot of the writing efficient code and so on. If you're a compiler writer, then you're definitely going to need to understand these things very clearly. And they're not completely useless, but they tend to be not as important. But the distinction that's really important here is the distinction between things that are R values and things that aren't. Or sorry, is that right? Yeah, things that are things. Let me get this right. Sorry, things that are L values and things that aren't. In other words, we don't really care about the GL value term here. We're basically going to kind of focus on L values, pure R values, and R values, and then X values kind of come along for the ride because they're involved kind of indirectly. So anyway, that gives you a little bit of a basic idea about the value categories. But I have a lot more to say about what these different categories of expressions, what their properties are, and so on. The reason why we care about value categories is that when we're trying to make a distinction between, like we're looking at some chunk of code and we're trying to figure out, based on the rules and the language, is it going to move or is it going to copy? It turns out that what this comes down to is the source for the move and the destination for, the source for the thing that could be either moved or copied and the destination for the thing that's either being moved or copied. It comes down to, is it an R value expression or an L value expression? And then if it's one of these things, then it will move, the other thing will copy, more or less. So this is the reason why we care about L values and R values. Basically, it comes down to understanding how moving works versus copying. It's a big issue here. And although this is getting into, like, admittedly a finer point of the language, this is something that definitely you are responsible for, because otherwise, if you don't understand this, you're going to have a lot of problems with respect to making moving and copying work properly in your code. Also maybe testing it, because when you want to test a move, you need to make sure it's moving and not copying, and then how do you make sure that happens? And probably there'll be something, well, almost guaranteed something will show up on the final exam with respect to L values, R values, and stuff, because it is kind of important, at least if you're writing kind of more advanced code where you care about performance. Anyway, maybe that's enough said about maybe the first part of the slide. The other thing I need to talk about is the notion of identity. Just in general, if you have some kind of entity, it could be like an object, it could be like a function or some other entity in the program. You can talk about whether it has an identity or not. Maybe taking an analogy, kind of forgetting about code and so on, like maybe of people. People are some type of entity, like kind of a living life form. And suppose that people only had first names. Obviously my name's Michael. There might be another person whose first name is Michael in the class, I'm not sure, but it's a fairly common first name, right? But even if there was another person whose name was Michael, and clearly you could distinguish me from that other Michael, right? It's because we have, although we have a sense of identity, there's an identity attached to these things. Whereas there are some things where maybe they have the same value, like you can think of the name, like think of me like a variable, and my first name is my value or something like that. There are some things where that have values where if their values are the same, you can't distinguish one from the other. For example, in your code, if you have like an integer literal 4-2, like all integer 4-2s are the same 4-2. Like you can't say one is different from another. They're completely indistinguishable from one another. So some things may have identity, other things may not have identities. And this notion of identity is kind of important with respect to when we're talking about L values, R values, and so on, because it's partly baked into some of the definitions I'm going to talk about later. Just as an example, if we're talking about objects like variables, if a variable has a well-defined location in memory, in other words, you can unambiguously say it's stored at this address in memory, it must have an identity. The reason why is, like, I have two variables called X, but I'm not sure whether the same X or whether maybe one's a global variable, one's a local variable of a function. They're both called X. I can always distinguish one from the other by taking their address and checking to see, are their addresses the same? Are they stored at the same place in memory, provided that they have a well-defined location in memory? I mean, the issue is if they don't have a well-defined location, maybe the act of taking its address is not legitimate. I'm not allowed to do this. And for some circumstances, you can't take addresses of things. But if I could, because they do have well-defined addresses, I can compare the addresses and see if they're the same thing. So this is just an example to kind of further illustrate the notion of identity, but in the case of variables. And predominantly what we're interested in when we're talking about moving and copying are objects. I mean, lvalues and rvalues are properties of expressions. Objects are expressions. Like if I write x, it's an expression. But also I can have things like a plus b. This is not an object, it's an expression. But mostly what our focus here is objects, because we're interested in whether an expression that corresponds to an object is an L value or R value. So we can say something about whether moving or copying happens. Anyway, so first of all, L values. What exactly is an L value expression? Well, an L value expression is an expression that denotes a function, object, or bit field. And you can kind of ignore the bit field case. We're not going to talk about bit fields in this course. And they're not usually used that frequently. They introduce kind of a lot of special edge cases in the language and so on. So just basically forget about them here. We're basically interested in predominantly object part is really what we're interested in. And the L value is expression is something that has an identity. And because it has an identity, if it's an object, it has some kind of well-defined location in memory. We can take the address of something that's an L value expression, either a function or an object that has some well-defined location in memory. There's a little bit of a caveat here, though, is because you can overload the address of operator. In principle, you could overload it so it doesn't actually give the address; it gives some other thing. So as long as there's not like weird things going on like that, you can, in principle, find the address of something. Anyway, so that's why it says in some cases you can determine the address because of things like overloading address of operator. The other thing that's sort of baked into the notion of an L value is that it's not guaranteed to be safe to use as a source for a move. So if you're contemplating trying to move from something and that something corresponds to an L value expression, you cannot safely say without a lot more information whether you can safely move from it. The reason why is if you think about what it's saying, if it's a variable with a well-defined address in memory, if you move from it, what's the downside of moving? Well, the downside of moving is you're obliterating the value of that object, potentially, right? So how could things go wrong? Well, if no one ever looks at that value you've just obliterated, nothing could go wrong, right? If no one observes this mutilated value of the variable, nothing could go wrong. So what you're looking for in cases where it would be dangerous to replace a copy with a move is, could someone else observe this mutilated value and then use it in the wrong way, basically? They're using it thinking it wasn't mutilated. Well, what would be required in order for someone to use this mutilated value of the variable? Well, they need some way to access it. So if you have a variable that has a well-defined location in memory, anyone that knows that address can look at that variable, right, anytime they want. You have a pointer to it, you just dereference the pointer, go there. Or if you have a reference to it, you just access it through the reference. So typically, if you have something that has a well-defined location in memory, it becomes problematic or very, very dangerous to try to say, I'm going to use it as a source for a move. Because then anyone that has that address, that knows where that variable is stored in memory, could then observe that mutilated value. And you would have to make sure that none of the code that might observe it could possibly do the wrong thing. And in practice, probably you can't make such a guarantee. So this is the reason why sort of baked into this notion of L values is the fact that it's not safe to replace a move with a copy if the thing that you're moving from corresponds to an L value expression, because someone else might observe the value has changed and then thinking that it didn't change and do the wrong thing. That makes sense? So some examples of L value expressions. This basically kind of lists off some of the different examples of things that are specified as being L value expressions. So any named object, so like basically a variable that has a name. So this excludes temporary objects, right? Temporary objects don't have names. But any named object, like for example, in this code down below here, we have a named object I, a named object J. So for example, I here, this I is an L value expression. Not the whole line, but just the portion of the line which is I. J is an L value expression. I is an L value expression here. Get underscore value, but without the brackets, just the name of the function, get underscore value. This is an L value expression. If I add the brackets, that's not the name of the function. It's the return value of the function, essentially, the result that's produced by the function. So we have to make a distinction here. So get underscore value is an example of an L value. And by the way, the ones that are marked with stars here are kind of the ones that are more important in the sense that they're the ones more likely that you hit, that you care about, at least in the context of this course, and kind of on average are kind of more common. The result of calling a function that its return type is an Lvalue reference type is an Lvalue. So in this case, for example, we have a function called get_value. The return type is an Lvalue reference to something. It's an Lvalue reference because there's a single ampersand. If there are two ampersands, that would be an R-value reference. Single ampersand, Lvalue reference, double ampersand, R-value reference. So this function returns a result which has a type which is an Lvalue reference type. So in the code here, like get value bracket bracket, like ignoring the plus plus, but just the get value bracket bracket, this would be the result of a function that returns an Lvalue reference type. Therefore, it would be an Lvalue expression. And in the language standard, if you're trying to increment an integer, it must be an Lvalue expression. You can't do like the pre-increment operation on an R-value expression. Another example of an Lvalue expression is a string literal. Most literals, like basically all literals other than string literals in the language, are not Lvalues. Lvalues is sort of a special case in terms of literals. But this just sort of makes sense, right? Because essentially a string literal, probably the way it's going to be implemented by the compiler is it creates some array in memory somewhere and sticks those characters into the array. So there's probably going to be some well-defined address for that character array, you would think, and that's what the case is here. So for example, hello in double quotes, and the value of a string quote in like string literal like this is the address of the first character, essentially. Actually, I guess more formally, it's probably an array of characters which then can decay into a pointer. But anyway, maybe forget what I said because I don't really want to talk about some of that stuff like decay and stuff. Anyway, but this is an Lvalue expression here. Maybe a less interesting one, but it's helpful to just point out an important misunderstanding that sometimes students have here. Here we have an R-value reference to I, or R-value reference to int. I is an R-value reference to int. And then we're doing something like we're saying int j equal to I. The expression I here is an Lvalue. It's an Lvalue because I is a named object, essentially. It's an object with a name. I is an object. It's a variable, it has a name. But a common misunderstanding is people go, well, but I is an R-value reference to int. There's a word R-value somewhere in there. This must be an R-value expression. This is, I think, just deliberate sabotage on the part of the people who design the language to make it hard to understand. Because you have like two things that are kind of being confounded here if you're getting confused about what I just said. In other words, if you're inclined to say, I think I is an R-value because I here is defined to be an R-value reference to int, you're confounding two things, which is there's value categories, which are things that have to do with expressions. An expression has a category. It's either R-value, well, R-value or Lvalue, or R-value, X-value, PR-value, depending on how finely you want to kind of split things up. And then types, totally different thing from expression. Types can be like, you know, an R-value reference to something, an Lvalue reference to something, and so on. So you want to keep clear here the difference between a type and a value category. They're kind of completely separate things, but unfortunately, because there's kind of a little bit of an indirect relationship between R-value references and R-value expressions and so on, they chose to like kind of can mix up these terms. So it's kind of, I think in some, I'm maybe being a little bit facetious when I say it, but it's almost as if they deliberately just tried to make the language hard by doing this. But anyway, don't mix up R-value reference type, like a type of R-value reference to something as part of a type of a variable compared to an expression that is a R-value type expression. They're completely different things. Anyway. And I guess this is a good time to stop here because we're just running out of time. Any last questions?